today. So I've got a couple of other questions that were coming in, and feel free to keep entering them. But to start things rolling, so let's see, Bill Botke has a question. The argument used to rule out the late veneer could easily be flawed. If the projectiles delivering the water are large, the Earth could get a lot of projectiles the Moon would never see. The highly siderophile elements are completely consistent with such results.
And let me note that each individual can scroll that document and it doesn't affect the other screens.
There was also a discussion started by Mark Hirschman that was asking Steve Desch, how can we reconcile the high supposed temperatures of the protolunar disk with the proposed cold silicate core of the early Moon? Steve answered, but maybe you'd like to actually speak, Steve. You're on the line, are you not? Are you not on the line, Steve? No. There you go. Okay, so Steve's calling in. Did I miss any questions? Is there any other? Got that.
Hi, well, I guess I have a question, but it goes back to Alberto. Is that okay?
Yeah, it's okay while we're waiting for Steve.
Okay. So I was trying to type it out here, but I'm confusing myself because I only have one line to read. So I guess my question is about the extrapolation to the whole Moon. The conditions under which apatite are crystallizing is, they're late phases, so they're accessory minerals, so they're kind of picking up a lot of the junk that's left over. And then also the volcanic glasses, they're coming. They require some volatile source to drive them out from their deep source and drive them out molten, so that they're glass. It seem like they're very unique conditions where you would have a bunch of sequestered volatiles. So that's why I'm asking how would then you extrapolate that to the whole Moon, if knowing that, or at least assuming that these are these unique sources.
So that means that you don't believe much of the data that comes from apatites? That's what you're telling me?
No,
so you think that the concentration of water that apatites are showing is consistently very, very high in most of them. It's true that they can pick up stuff. It's hard to analyze. Dealing with the apatites is very hard, but so it's hard for me to discard completely all that. So if I consider the apatites from the mare, and then I consider even not only the apatites from the mare, but also apatites from early cumulates, like the alkaline cumulates that Greenwood show, then I would suggest that it's not only the picritic glasses will carry the water. The question that you could ask and you can say is, well, hold on, but if all these things pass through crypt, and crypt was the only thing that has water, although there are some groups that says that crypt didn't have any water, then it becomes really, really complicated. The extrapolation is just very simple. We just try to look at the three different compositions that we see as an extreme. We are measuring now Apollo 14, and the Apollo 14 goes from very low to very high titanium, and they have also much, much higher concentration. Unfortunately, I cannot show it to you, but they have much higher concentration than we saw for the Apollo 15 and Apollo 17 for the water content. So even if we are trying to be as conservative as possible, that's the reason I said it's hard for me to argue for the 400 ppm that people are claiming. Even within the paper that we wrote, we said it could go from 79 ppm to 400. People are beginning to pick up the 400. And I think that it's probably closer to 100. Can I guarantee it? No, I cannot guarantee it. That's what we think. But
right.
if you put all the data together, it seems to indicate that yeah, I will be comfortable with 100. The question is how representative are the samples that we did by the Apollo mission and things like that. We need more samples, and we need to analyze more samples from what we have. But that's the extrapolation that we make.
Yeah, and I don't mean to give the impression that I'm criticizing any of these extrapolations.
No. It's a good question. I mean,
I'm actually becoming of the opinion of where is the water actually? Why isn't it closer to Earth's, or well, it does appear to be coming closer to Earth's, and also I'm not really sure how the for the appetite measurements, how then that is modeled to go back to what the source was for those appetites, because again, I'm not invoking creep. I'm just saying that the appetites, when they crystallized late in after the source melted, and they crystallized late, so they're in these conditions where you're having some of the incompatibles, and water is going to be an incompatible, so it's going to be rich at that time. Now,
that's correct.
If they're properly actually going back to following the entire crystallization sequence and can go back and say, okay, yeah, but then we consider all these other minerals, and they're showing us that, well, the apatite was probably, or the original source composition water was probably over here. That's fine, but it seems to me that maybe that's not being considered because it seems really complex. So
yeah, absolutely. I think that's the reason the people in England are doing a lot of analysis. They are doing a lot of experiments right now, trying to understand what is the partition coefficient, how the water will partition into apatites, at what compositions, and how that affected. We need experimental data, and we need, it's hard. When you deal with apatites, I find it hard. Also, you have the latest paper from Hui, I don't know if I'm pronounced it correctly, that measure the water in plagioclase from anorthosites, right? And they came up with concentration for the lunar magma ocean. That came up, I think, last year. Concentration of the lunar magma ocean around 300 ppm. Now you could say, yes, those analyses are extremely difficult with FTIR because they need to see the peak of the water at 2 ppm. I do agree with all that, but it seems to be, everything is just pointing to the same direction, whether this is a bandwagon and we need to revisit again and be careful with the data or not. It's just hard. It's just we are riding this wave, and we need to be careful. The best we can do is to try to be as careful as possible.
Thank you.
Okay, I see Steve has joined us now. Steve, do you have some comments for Mark?
Yeah, so Mark raises the question of basically how does the moon form? Can it form cold? And there's a lot of stages past the one I discussed in my talk that have to take place before the moon forms. And one of them that I didn't focus on today, but which I worked on and talked about at LPSC 2 years ago, is the stage where it loses volatiles from the disk. And that is going to happen by hydrodynamic escape, but it's very difficult to lose it by hydrodynamic escape. And that's where you drive a thermal wind, basically, where you lose everything that's in the atmosphere all at once. And if you don't lose it that way, you're not going to lose volatiles because you only have 100 years before the moon forms and the disk cools. And but it's very hard to lose volatiles during this stage. It has to be very far from the Earth, or else it's just going to fall back on the Earth or and be mixed in. Or and it has to be relatively cold, or else you're going to have a lot of SiO vapor that isn't going to that's going to keep the molecular weight of the gas high. That's bad for escape. And so you need a stage where it's sort of cooler and it's mostly water, and maybe water can dissociate in the atmosphere. That lowers the molecular weight, but then it still has to be warm enough to escape. So, I mean, there's a lot of threading the needle issues in order to get anything to be lost from the proto-lunar disk. That's something I talked about 2 years ago, and I'm continuing to work on. And then after that, okay, you've lost some of the atmosphere. You have this magma. The moon presumably forms from whatever's left in the magma, but this stage isn't really well understood. It seems as if it has to cool and form solids and lunatesimals, and that these can grow just outside the Roche limit and then migrate outward and sweep up other material. And so it's possible that you form a core that is formed from material kind of closer to the Earth, and then the later stuff that's added to the Moon could be cooler material from further out in the disk, and maybe that suffered more escape of volatiles than the stuff closer in. These are a lot of issues that have been raised in literature, and we don't know a lot about them, but I'm just trying to focus on the earlier stages of the disk and try and get at the volatile inventory then. Hello?
Sarah, I think you're muted.
Sorry, I'm on mute. I was thanking you and asking if there were anybody else who's online that have comments.
I have a comment for Bill Bodke. I don't know if Bill is still connected or not, but Bill sent a message before saying that the lay veneer could work as a large impact that will not see much of the Moon, and therefore will produce the lay veneer. I have no problem with that. The only problem is to argue for the lay veneer to be the origin of the water on the Moon. If that's what we see, if the water that we see on the Moon is produced by a lay veneer, I should see an associated platinum group element enrichment, and what we see is not that. We see a difference of around, like I say, 5 to 10 maybe between the water on the Moon compared to the Earth, but based on Day paper in 2007, they see 2,700 difference in the flux based on the PGEs between what we see on Earth and we see on the Moon. So we cannot put the PGEs and the water together by the same process. That's all what I wanted to say.
Well, it looks like Bill has another question here about Zach Sharp's work with chlorine measurements, and would like to have someone discuss, maybe you can discuss, Alberto, why the large abundances of water discussed here are discordant with those measurements.
Yes, I think that the way to consider this is because hydrogen, I guess the chlorine measurement, I don't know if he's thinking about the isotope of chlorine. Essentially what he sees is that there is a very large fractionation of chlorine isotopes, and that cannot be in the presence of water. The key here is to think how fast water will degas compared to the chlorine. By the time that the chlorine begins to degas significantly, probably most of the water has gone. And you can see it based on the measurements that we do for the lunar glasses, the concentrations of chlorine and the water indicates that the water goes way, way faster than the chlorine. So when the time of the water degas 100%, and this is just calculations with not precise data, probably the chlorine begin to degas, probably 20 to 30% of the chlorine is degas or something like that.
Carly, remind me, we were supposed to end at 12:40. I think we were just about out of time.
Yeah, people are supposed to have a little break between now and the next session, which is actually the last session of the Volatiles workshop. So we probably ought to give people a chance to do that. Greg, did you want to say anything about the next session?
No, not really. I don't have any introduction prepared other than I think this is where we go from the scientific to the practical in terms of how we're going to access and use the volatiles. So it's going to take a little bit of a change, and I'm looking forward to hearing what the speakers have to say.
Okay, I have one thing to add to that, and that is that we've noticed that not everyone registered for this. We have a lot of great participation, but we don't have email addresses for everybody that we would like to have. So if you were one of those who did not register, would you please send us your email address? And Brad Bailey has been sending out notes to people in the chat session, but you could do it by email as well. So however, just please be in touch with us today. Thank you.
I have a technical question.